In section 2.2, we're going to talk about the relationship between sequences, limits of sequences, and limits at a particular point of a function. And we start with theorem 2.1 that says we take a given function with domain capital D going into the real numbers, and x0 is going to be an accumulation point of the set D. So it doesn't mean that x0 is in the set D, but any neighborhood around it, any little epsilon or delta neighborhood around it, would contain infinitely many points of D. The function f has a limit at x0 if and only if the following is true. For each sequence xn that's made up of elements from the domain excluding x0, for each sequence like that that converges to x0, the sequence f of xn converges. I would like to have changed the wording of this a little bit, based on things that we can simply deduce. And actually we'll see in the proof that we could have made this a little stronger sounding. Notice what's missing is an actual limit, like a capital L, a real number that's the limit. It turns out that if we're to say the function has a limit at x0 and call that capital L, well, in the second part of this, for each sequence that converges to x0, this converges, this would converge to capital L. Each sequence converging to x0 would produce this sequence of f of xn's that would converge to the same number. Okay, so I thought about changing it a bit, and I think anytime we reference theorem 2.1, we can simply assume that the limits are the same. So whatever that limit is of the sequence at x0, that's the number that this sequence converges to. And we'll see that in the proof. Okay, I'm going to do just one direction of this proof. I'm going to assume that the left-hand side is true to prove that the right-hand side is true. So since f has a limit at x0, I can say, let's let capital L be that limit. So capital L is the limit of f of x as x approaches x0. What I have to prove is that an arbitrary sequence that converges to x0 will produce this sequence. So I'm going to say, let's let xn be such a sequence. Let it be a sequence in the domain that excludes x0, and let's let it be such that xn converges to x0. So that's an arbitrarily chosen sequence. All we need to prove now is that f of xn converges. And we'll show that, let me write that down. We will show that f of xn, that sequence, converges to capital L. If you can't read that, this is my sequence here, f of xn's, as n goes from 1 to infinity. Well, using the definition of what it means for the function to have a limit, what's the first thing we need? We need an arbitrarily chosen epsilon greater than 0 to be given to us. And now that we have that, and the fact that I know this limit exists, I can say, since f of x, I'm using a slightly shorthand here in a sense, although it might actually be more writing. Since f of x goes to L as x goes to x naught. Just another way of writing this. Where's the limit? Right here. As x approaches x naught, f of x approaches the limit L. Because of that, there exists a delta greater than 0 such that the following holds true. Just using the definition. X being in the domain and x being close to x naught, which we'll write like this, x and x naught are within delta of each other. That implies that f of x minus L is less than epsilon. I'm going to refer to that statement as number 1. Again, the justification for that is because this limit exists. Since xn is a sequence that converges to x naught, there exists a capital N, remember we're dealing with sequences now, such that if little n is bigger than or equal to capital N, that implies that xn and x naught are, let's see, that implies that xn minus x naught, that's the x naught is the limit, is less than delta. Normally we would see we'd use an epsilon here in the sequence proofs, but we're going to use the delta that we're given. And I'm going to call that number 2. Statement number 2. All right, for the final statement of this direction in the proof, we have thus n greater than or equal to capital N. Notice what that implies. What we just wrote, this would be less than delta. But if that's less than delta, right here, we know that this is true. And that's going to finish up the proof. So that implies that, well, by transitivity, this implies this, and this, that implies this right here. This implies that. So I'm going to say that n greater than or equal to n implies this right here. The only difference will be that it's an f of x n right here. And I'll state that that's by 1 and 2 together. That's the justification for that. And that means that what we wanted to prove, f of xn converges to L. I'll write that as a sequence. Kind of a two-step proof. And I mentioned the other direction I'm not going to prove, although I believe that proof is in the book. But there are two basic steps. Step 1 would be show each such sequence f of x n's converge to the same limit. Converges to the same limit. It says for each sequence it converges. Well, the first thing we would do is we'd show that it converges to the same limit, and then step 2 is just show that L is that limit. Each sequence converges to the same limit. I'm even going to say, call it L. And it happens to be the same L as we defined up here. And the second part would be basically a proof by contradiction. If you assume that you could have two sequences converging to two different numbers, you could easily reach a contradiction.
So how would you do the first step when you were doing it?
First step, show each sequence converges to the same limit. Suppose that you have two sequences converging to different limits. Proof by
contradiction.
Sure. Show that let's see, there could be a direct way to do it, but show that each such sequence converges to the same limit. Yeah, that would be the classic contradiction proof. Prove that you have two of them going to different limits and show that that's impossible. And then show that that shows that they all converge to the same limit. And basically I called it L. And then show that that number L is the same one that we had from above, which was that. Anything else?